So in this section, we're going to look at something called the factor theorem. Okay, so you would have seen it GCSE and before that and earlier on in the course. Very simply, firstly, if we have this quadratic, for example, as an example, x squared add 3x plus 2, we could factorize that, and then we wanted to solve it equal to zero. We could solve that by factorizing, and that factorizes to x plus 1, x plus 2 equals 0. And then we solved this by setting each bracket to 0. So the roots I get are x is minus 1 or x is minus 2, and they're both the roots of the function. As a reminder, the roots of a function, if we, or some sort of equation, is f is the values of x, right? Such that f of x would then equal 0. Well, here this expression equals 0, so these are the roots, okay? Kind of synonymous to solutions, basically, but it's the fancy way we call a solution to an equation, okay? So that will come into play in a minute, but as that's just a reminder. Okay, so why am I bringing this up then? Well, um, we've seen with any type of quadratic or polynomial in general, actually, that you can factorize it if you can. You can factorize it, and then from the factorization, you then can find the solutions, the roots, right? If you set it to 0. And what happens is we can essentially go from finding the factors to then going to find the solutions because you set each factor to 0. Okay, I might be kind of stating the obvious here, but it's important to really to when we go on to the factor theorem, it'll make sense why I'm explaining it like this. But we can essentially jump from the factor to the roots, okay? And we can also go backwards as well, because we saw some examples where we found the roots and we needed to find like the factors or the original expression. So then if we say we had x is 2 or x is minus 3 as two solutions to a quadratic, say, we could then work backwards to say that the factors were x minus 2, x plus 3 equals 0, right? And so what essentially happens is, and hopefully you notice, is that the bracket, what's inside the factor, actually the solution is kind of like the opposite, right? Because I'm setting the bracket equal to 0. And so I get this sort of result, this sort of mechanism, this sort of way of jumping from from the brackets or the factors to finding the roots, okay, very quickly by just setting each factor to 0, and then I can work backwards as well, okay. If I'm given the roots or the solutions, I can find the factors, okay. So that's kind of hopefully fairly intuitive. Hopefully that made sense. We've seen this before with GCSE. You've seen how we can actually factorize an expression, and then we can use that factorization to then get the solutions very quickly by setting each factor or bracket to 0, okay? And we can work backwards as well if needed to work the factors from the roots. Okay, so I think that's not an unfamiliar concept. Well, what this sort of theorem does is kind of put that into words, this sort of idea into words. And so I'm going to state it now. So the factor theorem here. So what am I going to say then? Well, what we have then is any given bracket, obviously in this example with x plus 1 and x plus 2. What if in general we had a factor x minus a? So then I'm going to say if we have a function f of x here, which is where this is going to come into play, where I wrote this down. If we have a function or an equation, if we have f of x equal to 0, right? That's my equation, that's my function, right? Therefore, I want to find the roots or the solutions to this, okay? If we have that, right, if we're solving an equation equal to 0, you know, a fairly normal thing we normally do, right? Well, firstly, then we could, if we can find the factors, Again, here we could factorise. Obviously, we know how to do that. For example, we found two numbers at times to get +2 and add to get 3. It turns out we get these two factors. But in general, if we have a factor, so if and so again in these examples, the factors were x plus 1, x plus x plus 2. If we generalise that to say x minus a, and you see what's minus in a minute. But if you have to say x minus a for any number a whatsoever, so it's sort of a general factor, right? Just any factor x minus a. If that is a factor of our original equation or our function, okay, then, well, think about this example again, right? If we then got the factor, we could jump to then getting the corresponding solution from that bracket or the factor, because we set the bracket equal to 0. Okay, so again in this case, I got this solution x plus 1 from the bracket, because x plus 1 equals 0. Therefore, if I solve that, I get x is minus 1, which is that solution there. If I set this factor to 0, x plus 2, that would then be x plus 2 equals 0. Therefore, x would be minus 2, which is the corresponding solution there. So really then, I'll just set the bracket to 0. So in this case, in this general case of x minus a, that would mean x minus a equals 0. Therefore, the solution or the root is x equals a. Okay, if I add a to both sides. And so that's it, right? So if that's a factor, then we can conclude that x is a solution to to the equation, right? And again, it might seem like a fairly kind of obvious result, but we'll see. It does come in handy to state it like this in a minute. So it's a solution to the equation. But what we can also say by using this sort of function notation up here again, a root then, well, that's it's our input, it's the values of x such that f of x would be 0. So if then we say x is a a root, that means if we plugged in a for x in our function, we get 0, hence it would be a solution. So what we can then also say is that actually therefore f of a would be 0. Okay, if I plug it in a into the function, I get 0. So then I can alternatively say that f of a would be equal to 0. Okay. So in general, what we would then get is, if we have a factor x minus a, then we can deduce the solution is f of a equals 0. Okay, so if x minus a is a factor of f of x, if we know it's a factor, then we can say that f of a, the function at a, would be equal to 0. So a would be a solution there. Okay, and actually, like with this example, then we work backwards. Where given the roots, we then deduce the factor. So if we had x was 2, then the factor was x minus 2. We can work backwards with this statement as well. And instead, if f of a equals 0, so if we're given a root instead, so if f of a equals 0, so a would be the root, then we can work backwards and say that x minus a would be a factor of f of x. And that is the factor theorem, plain and simple. Okay, so it's a sort of maybe obvious result. I'd imagine we kind of implicitly used the factor theorem already when we solved all sorts of polynomials, quadratics. When we solve by factorising, we're implicitly using the factor theorem to get a solution. But yeah, so guess sort of obvious result, but you'll see in a minute why it is helpful to write it, to actually write it explicitly like this, because certain questions, it's very helpful if you have this sort of like explicit result, right, which you can not substitute in. We'll see examples in a moment. But yes, that's a factor theorem then. So essentially, if you have a function, and then we set it to 0, so say you have an equation equal to 0, like a quadratic, again like the one we just saw up here. For example, that quadratic equal to 0. Then if we know a factor of that equation or the factor of the function, then we can deduce the corresponding solution, which should be then x is a. Okay, and also I said it was negative here because then it makes it quite cleaner to write the solution, because if I said x plus a here, the solution would be x is minus a. So I just have to flip the signs, but it looks a bit uglier if I did it that way, so I'll just say x is a and the factor will then be minus a. Okay, there we are then, and then we can go the opposite way. If we're given a root instead, so x is a is a solution, then we can deduce the factor would be x minus a. Okay, and that is it, plain and simple. Cool, so we're going to look at some examples then, and it's a very important topic as well. It comes up for every year exam wise, so yeah, but it's not a bad topic. Anyway, let's have a look at some examples then. We need to show that x minus 2 is a factor of x cubed plus x squared minus 4x minus 4 by, firstly, algebraic division. Now, we looked at algebraic division last time, if you need a refresher. But then that same, by algebraic division, we need to then divide this cubic by x minus 2, okay? Okay, so x cubed plus x squared minus 4x minus 4 divided by x minus 2. Okay, but then again we need to set up a bus stop, so the divisor, the denominator, right, is outside, and then inside the bus stop is x cubed plus x squared minus 4x minus 4. And then we said, well, what's the highest power or the highest term inside the bus stop? That's x cubed. So then we did x cubed divided by the highest power outside the bus stop. That'd be the x term. And so we do that x cubed, the highest there, divided by the highest here. X cubed divided by x is x squared. That will then be up here. And then we then multiplied x squared by everything outside the bus stop. So then x squared times x is x cubed. And then x squared times minus 2 is minus 2x squared. Take them away, then x cubed take away x cubed will be 0, which is what we want. Then x squared take away minus 2x squared, that's a double negative, that'd be x squared add 2x squared, which would be 3x squared, okay, plus 3x squared. Alright, and then we need to bring this next term down, minus 4x down here, and then we repeat the process. So what's the new highest term? Well, it's here now, 3x squared. Then we do 3x squared, the highest term we have, divided by x, the highest term outside. That will then be 3x. So then we say plus 3x here. And then we do the same sort of thing then. So we then do 3x times everything outside. So 3x times x will then be 3x squared firstly. Again, we want that because then they're the same, so they cancel out. And then 3x times minus 2 would be minus 6x. Then again, if we take both sides away, 3x squared take away 3x squared is 0. And then minus 4x minus 6x. Well, that's a double negative. So minus 4x add 6x would be plus 2x. There we are. And then we need to bring this last number down, so it'd be minus 4. And then what's the highest term we have now? Well, it's the 2x, right? That's the highest power of x. So plus 2x. Oh no. No. Because what we have to do then, oh god, is the 2x, the highest power, needs to again divide by the x, the highest power outside. So 2x divided by x is 2. Cool. And then we do the same. So then 2 times x minus 2. Well, 2 times x is 32x. And again, 2x times... No, 2 times minus 2 would be minus 4. There we are. And then we take them away. So then 2x take away 2x is 0. And minus 4 minus minus 4, that's a double negative. So minus 4 add 4 then would also be 0. So overall, I get 0. Okay, and remember, this was the quotient, the thing on top of the bus stop, and that's the remainder. That's how much we have left over. And so the remainder is 0. That means there's nothing left over, which means that this quotient has to be a factor, as well as this, right? This x minus 2. So no remainder, hence x minus 2 is a factor, okay? And you can see that as well, because remember, we can write any fraction like this, any division, any polynomial division. So x cubed plus x squared, take away 4x, take away 4 over x minus 2. Then that's the quotient. Add our remainder over x minus 2. So how much do we have left of x minus 2 after we divide? And well, actually the quotient is, as we remind up here, x squared at 3x plus 2. And our remainder was plus 0 over x minus 2. However, if that's over 0, then that's just nothing overall. So that's what we're left with. So then, if we then times the cross by x minus 2 to both sides, then simply x cubed plus x squared minus 4x minus 4 would be x minus 2 times this quadratic x squared and 3x plus 2. And so hopefully then you can see it's split into 2 factors, okay? And there we are. So that means x minus 2 must be a factor when there's no remainder. Cool. There we are then. And so, yeah, you can use polynomial division to find the factors of a certain polynomial, okay, in that way. We looked at that last time though, but yeah, so no remainder here after you've done the division means it must be a factor. We're dividing by a factor, okay, cool. Then part B then says alternatively show that this is a factor by the factor theorem. Okay, so that's what we're going to be just looking at. So let's do it here. So it's saying to show that x minus 2 is a factor of this cubic by the factor theorem. So we need to show it's a factor, okay? Now let's go back to what we wrote up here. And it was these two things essentially. We have a function, we have an expression f of x. And so it said if x minus a is a factor, then the solution to the equation when it's equal to 0 is a, okay? Well, in this case, if it was x minus 2 is a factor, then it's saying x equals positive 2 would be a solution. But here we're trying to show it's a factor, not to show that there's a solution. So actually we need to go the other way and go and look at this second sort of bullet point instead. And then we have the opposite, where if we have a solution, so if x is a, so in here it'd be x is positive 2, right? So if x is positive 2 equals 0, then that means x minus 2 will be a factor, which is what we want, okay? So all in all then, what we need to do to show it's a factor is simply to calculate f of 2. Because if f of 2 is a root, then x minus 2 will be a factor via the factor theorem, alright? That is this second bullet point here, okay? And so that's what we're going to do. So we're going to simply then compute f of 2. So then f of 2, and what am I plugging it into exactly? What's my function? Well, it's this expression here, right? This x cubed plus x squared minus 4x minus 4. So that would be 2 cubed plus x squared, so that would be 2 squared. Minus 4x minus 4, so minus 4 lots of 2 minus 4 If you put that into a calculator then, you indeed get 0. There we are. So that means f of 2 equals 0. Therefore, by the factor theorem, then if 2 is a solution, then x minus 2 is a factor. And it would be a factor of the cubic, right? Of our cubic x cubed plus x squared minus 4x minus 4, okay? And there we are. So there we are then. So that is so it provides a much more efficient, quicker way of be able to compute or show something is a factor, right? Rather than just doing the polynomial division. So yeah, so polynomial division still is important because obviously, so you know, oftentimes you won't get remainder of 0. So that's where the factor theorem be useless, because the factor theorem requires it to be a factor. And remember, it's a factor when the remainder from the division is 0. So still remember the long division, but if you want to show stuff with factors or whatever, then the factor theorem is a much better method to use in this case. And we'll be using some more examples to really illustrate it. But yeah, there we are. Okay, we have this example then. We are given that x plus 1 is a factor of 4x to the 4 minus 3x squared plus a. Find the value of a. So again, this is where having the factor theorem written down is helpful, because now we know exactly what we need to use and what to substitute in. Anyway, so we are told that x plus 1 is a factor. Well then, what does that mean then? Well, that means that if x plus 1 is a factor, then again the root then would, what, you'd have to set the bracket to 0, so that would mean x would be minus 1. So x minus 1 is a solution. Or we could say alternatively f of minus 1 equals 0, where f of x is this expression here. Okay. Well, then that's what we're going to do. We're going to plug in minus 1, x is minus 1, into this expression here. And it has to be 0, because that would be a solution to the equation if it was 0. Therefore, then, 4x to the 4 would be 4 lots of minus 1 to the 4, minus 3 lots of minus 1 squared plus a. And that's equal to 0, right? Because that would be a root of the solution, okay? And so there we are. So we just plug that into a calculator. Well, we can work out the bracket. So 4 lots of minus 1 to the 4 minus 3 of minus 1 squared gets me 1. So that'd be 1 plus a equals 0. Therefore, a is simply minus 1. Nice. There we are. And again, this is also why this is better than the long division, because long division doesn't really work. Well, it could do, but it'd be extremely fiddly when you have unknowns in your expression. So dividing with unknowns in your polynomial and your division makes long division extremely awkward to use. So the factor theorem in this case, to deal with factors, is by far a better method to use, and hopefully it starts to become simpler to use and easy to pick up as we do more examples. Okay, cool. Example 6 then, we need to fully factorise 2x cubed plus x squared minus 18x minus 9. Okay, so fully factorise, so basically we need to factorise it into well, factors really. So if we had 2x cubed plus x squared minus 18x minus 9, it's a cubic, so we'd expect 3 factors of x, right? If we were to fully factorise it as much as possible. So it would look like x minus a, x minus b, x minus c, okay? Obviously, I don't know what these numbers a, b and c are, but that's what I'm going to expect it to kind of look like, okay? It's 3 different factors of x. But how do we get there? How do we find one factor? Well, again, if we can find one factor, then that means we can split it into a sort of quadratic factor, right? and I know how to factorize quadratics. So even if I just find one factor, then I can get a quadratic factor, because then obviously a quadratic here, x squared times x would be x cubed, so that would be the two factors, and then I can factorize this quadratic in the normal way, because I know how to factorize quadratics based on GCSE, and earlier on in the course I know how to factorize quadratics, but I just need to get this one factor before, right, to factorize it in some way to get a starting point. How do we find a factor then? Well, via the factor theorem, to get one particular factor, x minus a, well, I need to find a root, because that would mean f of a would be 0 in order to get a factor x minus a. So this means I need to find a root. And this is where the question is quite nasty, because they give you no hints whatsoever into where one root would be. Now, your calculator does, I discussed this for when we looked at quadratics, solving quadratics. Your calculator will have a sort of polynomial solver function. Basically means it finds the roots of a polynomial. Well, it can also solve cubics. Okay, we can't factorize this obviously immediately, because we can't factorize an x out, say. Okay, so we're quite stumped. So we need to appeal to the factor theorem to find a factor. So we need to find a root to find a factor. Anyway, to find the roots then, because then if we can find the roots, then we can factorize via the factor theorem. Now, usually questions, they do tell you one root, just so you don't, because basically what we would have to do at this point to find a root is literally just plug in, say x is 0, x is 1, x is 2, x is 3, and so on, right? We don't know, we have to start plugging in values of x, right? And maybe there might not be integer, I don't know. So but it will be one of these, because the questions aren't that mean. Okay, they're quite close to 0, so you don't have to try for many values. However, because of why I'm talking about the calculator solver function, it's because if we can then instantly find a root, then we can find a factor, no problem. So our calculator does the hard work for us for finding a root. So then you go on to your quadratics, your polynomial solver, which again I discussed in the quadratic section when we solved quadratic equations. So that'd be menu, option A, and then option 2. Polynomial degree will be 3, because it's a cubic. And so then you input your coefficients, so that'd be 2, 1 for x squared, minus 18, and then minus 9. And so it gives you the roots, if you were to use it using your calculator. X is 3, x is minus a half, x is minus 3. Okay, so they're fairly short roots. Okay, and you could have probably got them if you've tried a few values of x, right? The first few values of x, you probably would have got one of them. So that's the calculator though. However, obviously, you need to show you're working, right? Well, some mark schemes will probably mark schemes can be fickle. Sometimes they let you just write the roots down. Sometimes you need to show you're working. It's just best to show you're working. Okay, so we have these roots. Well, then we can deduce that the factors would be x minus 3. X minus a half would be plus a half, and then x plus 3. Those will be my factors there. However, I can't just jump to that, right? I need to show the method how to get there, because the calculator gives me the roots, but I need to show how I get those roots, you know what I mean? So what we're then going to do then is just take one of these roots. Let's take x is 3, right? But we're not going to say the root is just 3 with no backing up. We need to justify why it's 3. So how we justify it is then again the factor theorem, right? We then need to plug in x is 3 into our expression, right? So if x is 3, then f of 3, if we plug in 3 into here, would then get me 2 or 3 cubed plus 3 squared minus 18 lots of 3 minus 9, and put that in your calculator to check, but you should get 0 because it should be a root. Remember, a root again is the function, the expression equal to 0, so it'd be a solution to the equation if this was equal to 0, right? Anyway, put that in your calculator. And you get 0. So then I then can justify that this is a root because it's equal to 0, okay? So therefore, then we can say x minus 3 is a factor, okay? Now actually, you could do that for the others actually. You could, you know, as I said, the calculator gives you all 3 roots. You could then just input the other solutions where x is a half and minus 3, I think. You could plug in x is a half and f of 3 when x is 3, and they're both also equal 0. You could then justify that those are the 3 roots and then factorize it that way. But I want to show you a different approach after, instead of doing that, which will help with exam questions as well, because sometimes you won't be able to do that. Given on, you know, they might introduce algebra, which forces you to only have one, which means the calculator, you can't plug in algebraic values, right? It needs to be known actual numbers. Anyway, what I'm going to do then is, because we know a factor, so if you're ever in a situation where you need to find a root and of something that you can't solve, you know, by the formula or factorizing right off the bat, you need a root, right? Then you can use the calculator to help you tell you what it is, and then you can substitute that in to get it to 0. But anyway, we found a factor then, so that means that 2x cubed plus x squared minus 18x minus 9 is now x minus 3, and then some other polynomial, right? Because it's a factor. But then think about it. I have a cubic here, and I have a linear term. That means I need an x squared term. I need a quadratic factor. So it's going to be ax squared plus bx plus c. So I'm going to have a quadratic factor, okay? And this method, it does come up this sort of, what we call this is comparing coefficients, and you'll see what I mean by that in a minute. The whole idea is you match the if you're factorizing something like a cubic, you try and put the factors to match the powers of x, right? So if I have x cubed here and then I have x here, then I need an x squared factor, so I need a quadratic factor. Okay, so then then I need to find these values a, b and c, right? What exact quadratic factor do I have? I have a general one, but I need to find the exact numbers to get with this cubic if I was to then expand this these brackets, right, to get the cubic. Right, okay. Well, that's what we're going to kind of do then. Well, if this cubic is equal to this factorization, which it is, well, that means I could just really expand this, and then it should be matching the cubic. And that's the idea, right? Okay, well then that's what we're going to do. So then if we expand this, then that's going to be ax cubed, so if I times x by all the terms here, I have ax cubed plus bx squared plus cx, and then I'm going to times minus 3 by all the terms here, so then minus 3 ax squared minus 3bx, and then minus 3c. Oh, it's a bit off the page there. There we are, nice. So we expanded it, and so then the idea is that this cubic will be equal to this cubic now. They're the same. Right. Well, then that's what we're going to do. Comparing coefficients then, well, it means we compare the coefficients of all the terms, right? First, with the x cubed term, we have 2x cubed. So it's going to have to equal the x cubed term on this side. Right, the only x cubed term here is a x cubed. So that's going to equal ax cubed, and from that I can then deduce a would be 2, right? There we are, so I found the a value there. Then let's compare the next term, so the x squared term. Then, well, it's just x squared, right, on its own, so that's 1x squared. And then that's going to, well, then what are the x squared terms on the right hand side? Well, we have bx squared there, but we also have a minus 3ax squared. Therefore, from this, I can equate the coefficients, hence the name comparing coefficients, to then get 1 is equal to b minus 3a. But I know what a is. It's 2. So I can say it's minus 3 lots of 2. Then I can solve this for b. B then would be if 1 add 3 lots of 2, that's 6. So 1 add 6 would be 7. Okay. So then 7 take away 6 would be 1. So we found our b. Okay. Well then, I need to then find the, so I found a and b. Now I just need to find c. Now I could then say, well, let's compare the x term, so minus 18x. But actually, I can make my life easier, because what about the constant term, the number on the end? That's minus 9. Well, the only number on the right side, again here, the only number term with no x tag to it is just the minus 3c. So I get a very simple equation. If I compare the numbers on the end to minus 9 has to be minus 3c. Okay. Therefore, c, if I divide by 3, minus 3, sorry, gets to be positive 3. So there we are. We found out a, b, and c. Therefore, I can write this cubic in terms of these two factors. So 2x cubed plus x squared minus 18x minus 9 is x minus 3. And now the quadratic factor, and now we know our coefficients a, b, and c, will be 2x squared plus 7x plus 3. Cool. Right, okay, well then, it said then to fully factorise, which means factorise as far as we can. Okay, well, we could factorise a quadratic, right? So let's have a go with that. So I'm going to factorise the quadratic part, say, down here. Okay, so then I'm just factorising a quadratic. I know how to do those. I've looked at many examples how to do that. Well, again then, because we have a number on the end, it's not 1, it's 2, we need to then adjust for that by then looking for two numbers at time to get 6. Not 3, but 6, because 2 times 3 is 6, okay? And then we need two numbers that add to get 7, okay? To do that then, well, what's the factors of 6? Well, 6 and 1, they add to get 7, so I can get 7 from this factor pair, okay? Okay, so then from these two numbers, they need to add to get 7 and times to get positive 6. Well, it's just 6 and 1 then, right? 6 times 1 is 6, and 6 plus 1 is 7. So that is my, well, it wouldn't be my factors, but it tells me the way to split up the 7x, right? So then 2x squared adds 6x plus x plus 3. Doesn't matter if you put x first or 6x, doesn't matter. It factorises in the same way. So there we are. And again then, our usual method, but then we factorise the first two terms and the last two. So firstly, 2x squared adds 6x goes to 2x, and can factor out 2x between them. That'd be x plus 3. And then simply x plus 3. I can't do anything more with that. Well then, x plus 3 is a common factor, so then I can factorise even further, pull that out, and then I get 2x plus 1, and that is my factorisation. So there we are then. We can then further factorise to x minus 3, x plus 3, 2x plus 1. Great stuff. There we are. Cool. And so then part B, then head sketch the graph of y is 2x cubed plus x squared minus 8x plus 9. So it's sketching a cubic. And again, we know how to do that. We looked at that in chapter 4, where we looked at a graph. We looked at sketching cubic graphs. So if I do part B here, so I want to sketch y as x cubed. No, 2x cubed, sorry, plus x squared. Well, if it's 2x cubed, No, well, it's the same as this factorisation, right? So I'm just going to bring this it's the same as this factorisation. That's what I'm sketching. There we are. Okay, but I know how to sketch these, right? Because firstly, how do I sketch a cubic? Reminder. Firstly, I need to determine the shape of it. Is it a positive shape like that? Or is it a negative shape going down like that? Well, that's going to depend on the sign of the x cubed term. What's the x cubed term? Well, it's x here times 2x. That's 2x cubed. So it's positive 2, so it's a positive shape. There we are. So that's the sort of shape our cubic's going to look like. So if we draw our axis then. And then, well, what are the key details? Well, it's going to be our x, where it intersects the x-axis and the y-axis. Well, firstly, the y-axis here is when that's the easy one. That's when x is 0. But if x is 0, then y, if I plug in 0 into here, it'd be -3. And then +3, and then 1 there. Okay, so -3 times 3 times 1 is -9. So that is where it intersects the x-axis, so it'd be y-axis, which would be down here, say. There we are. And then we need to plot the roots. So again, if you set that would be the y0, so that's when f in equals 0. But that's when each bracket's 0, so that'd be the roots of 3 -3. And 2x plus 1 is 0, so 2x would be -1, so x would be -1/2. Actually, I think I should make it a bit more spaced out, actually. I'll put 3 here, 3 here, -9 would be like all the way down there somewhere. Okay, and then -1/2 would be here, say. Okay, cool. So now I've got the roots, or the intersection of the axis. So then lastly, remember, and then need to look at the roots. And are there any repeated roots? Well, no, okay. They're all singular, okay. There's no like squared or cubed brackets. What that means is then it's simply just going to cut through the axis at those points. So with all that in mind, and it's going to have that sort of shape, it's going to look a bit like this. And that's -3 there. There we are. Oh, that doesn't pass through -9. Oh, let me scroll down. There we are. There we are. That's what our cubic will look like. There we are. Cool. So yeah. So again, if you need a reminder on that, because again, with this course as well, if you've not looked at exam questions yet, they do tend to like to bring in multiple topics together. So even in this section, you need to know how to sketch certain graphs still, right? Remember, if you need a refresh on that, we looked at sketching cubics in chapter 4 of the AS Pure part, where we looked at sketching all types of cubics like that. But there we are, and actually this is a good reason why we need the factor theorem. It gives us a way to factorise complicated expressions, right? If we don't have a factor, we can then find the factors because of the factor theorem if we can spot certain roots. If we then can then factorise, well then we can deduce the type of roots, right? Are they any repeated roots? Which then affects what the graph will look like, right? So it helps with, for example, with graph sketching. Okay, so it's a very useful tool. But anyway, there we are. Okay, and then I'm going to leave the last example before we look at some exercises. We've got this. I guess it's sort of a sort of proof of the factor theorem. So we asked to prove that if x minus p is a factor, then f of p equals 0. That's basically the factor theorem, by the way. So we just need to prove that. Okay, well, very simply, we have f of x then. If x minus p is a factor, well then that's going to mean f of x can be written as x minus p as a factor of x minus p and some other function or g of x, right? That'll be another polynomial, right? And then if we times these two together, we will get back our original f of x. Very, very similar to the example we did previously, right? Where we had this whole cubic and we split it into the factor x minus 3 and then this other factor 2x squared plus 7x plus 3, okay? So that's sort of the idea here, right? If we say something is a factor, then that means it's a multiple, right? Very simply, it's a multiple of the function, right? So if it's a multiple, so it's x minus p times some other function, okay? That's just the literal meaning of that. Alright, very akin to numbers, right? If you said, for example, 8, well, 4 is a factor of 8 because then 8 is 4 times 2. But that's because 4 is a multiple. 8 is a multiple of 4, but 4 goes into 8, right? It's a very, very, very similar concept here. Anyway, hopefully you see we can write it in that form. Because it's a factor, we can express it like this. We don't need to know what this g of x is. It's very general, right? So it's for any function f of x, g of x, right? Which are polynomials. Anyway, we can write this. Okay, but then it said then prove that f of p is 0. Well then if we have f of x, let's see what happens when we plug in p. But then f of p, if I plug in p for x, that'd be then p, x will be p, take away p, times by g of x. Well, be g of p, right? There we are. Okay, well, we can actually simplify this bracket. P minus p is now 0 times g of p. But then 0 times anything is still 0. Therefore, f of p is 0. Well, hang on, there we are then. So it's a very simple thing to prove, really. But you don't need to know how to prove it, but there we are. It's quite a short, nice little proof behind that. By the way, we are looking at proof in the next section, so this is a good idea to warm up for that. But there we are. And again, this is the statement of the factor theorem as well. If you have a factor as a reminder, then that means it's a root, which means you plug in if you plug in p into the function, we get 0. Anyway, that's the factor theorem. Let's look at some more examples then. Okay, so we are given that x minus 1 is a factor of this. Again, we need to find the value of a. So it's very, very, very similar to the example we did earlier, but I want to do these to really emphasize how this works. If this is a factor of this, okay, well, we can use the factor theorem to say, well, if x minus 1 is a factor, then well, then x equals 1, right? If you set, is a solution, right? And again, that's akin to just basically setting the factors to 0. Okay, so then if you get x is 1 as a solution there. Okay, and we can say that's by factor theorem. Okay, cool. Okay, well then if that's a solution, but then we plug this in, x is 1 into here to get and make it equal to 0. So therefore 5 lots of 1 cubed minus 9 lots of 1 squared plus 2 lots of 1 add a, and if it's a solution and it's equal to 0, it's a solution to that equation. But then we just let's just put all that to a calculator. 5 lots of 1 cubed minus 9 lots of 1 plus 2 lots of 1, you get minus 2. Add the a is equal, and that is an a, not a 9. My a's look like 9s, don't ask. Plus a equals 0. Then I can add 2 to both sides, so therefore get a is 2. Cool, there we are. So there we are. And I would say as well, it is a really good idea to learn this particular type of question because it comes up loads of times. This exact type of question. This is basically an exam style question. So make sure, very, very simple. It comes up like question 1 on the paper, but don't lose easy marks, right? Hopefully that made sense, right? We'll look at a sort of hard example of this in a moment, but yeah, that does come up in exams, so it's very good to be able to get your head around what I've done there. It might seem simple, but don't lose easy marks, right? There we are. So let's have a look at this one, which is, I guess, more of a step up. So now we have two factors. We are given x plus 2 and x minus 3 are factors. Okay, so yeah, we have two factors then. So really, we're going to plug in these two numbers in, right? So if both x plus 2 and x minus 3 are factors, well then we're going to apply the factor theorem to both of them. So that means x minus 2, well, x is minus 2, and x is positive 3, if you set them all to 0, that means they're both roots or solutions. So then f of minus 2 equals 0, again if we call this f of x, say, and f of 3 will be 0 as well. Well, that's useful because we've got two different equations, because we've got two unknowns, okay, which allows me to find that. So that's what I'm going to do. I'm going to plug them both in. So firstly, f of minus 2, that's going to be then, if I plug in minus 2 here, my g of x cubed would be g lots of minus 2 cubed, plus h of x squared would be h lots of minus 2 squared, minus 14 lots of minus 2, plus 24. Then if we simplify that, well, minus 2 cubed is minus 8 g, and then minus 2 squared is plus 4h, and then minus 14 of minus 2 plus 24, that's plus 52, and again that would then be equal to 0. There we are. Okay, but then the other one I can plug in is that f of 3. And then that would be, if I plug in 3 into the expression, I have g lots of 3 cubed plus h lots of 3 squared minus 14 lots of 3 plus 24. And again, that simplifies to 3, well, 3 cubed is 27. So that's 27g. And then 3 squared is 9, so 9h. And then minus 14 lots of 3 add 24 is minus 18, sorry, so then that would be equal to 0, because obviously it's a solution, so it's equal to 0. There we are then. So essentially now these are simultaneous equations, right? Two equations here with two unknowns. We could solve them simultaneously. So how can I solve that? Well, it's not the nicest, right? The coefficients a lot of h and g are quite awkward to work with. Well, what we'll have to do then is to, again, I'm probably going to do elimination, say. I'm sport for choice how to solve these, but I think probably elimination might be the best way. So we're going to match the coefficients of, I'm going to say h, right? I'm going to match the coefficients of h, so I need to scale both equations. So I'm going to times the first one by 9 to then match the bottom one. So times up the first one here, that equation by 9. But then I get minus 8 times 9 is minus 72 g. And then plus 4h, that'd be 9 times 4 would be 36h. And then plus 52 times 9 is then plus 468 equals 0. And then I'm going to, for the second one then, if I want 9h, I'm going to try and match 4, so I'm going to times by 4. So the h's will be the same coefficient. Anyway, so then if I times the second one here by 4, 27 times 4 is 108 g. And then 9 times 4 would be plus 36, hence why I've done this, because they'll cancel out. And then minus 18 times 4 is minus 72 equals 0. Right, so now then I can take them away, and therefore I'm left with minus 72g, take away minus 108, I get minus 180. G, and then of course 36h take away 36h gets us 0, and then 468 take away minus 72, so that'd be a double negative. So 468 add 72 gets me 540 equals 0. So now we can solve that for G, right? So then G, well, if I move it to one side, I get 180G is 540. So then G is 540 divided by 180. And then that will get me, is it 3? Yes, nice, okay. Get a nice number in the end. There we are. So then I got G's 3, but then therefore I can find H by substituting that back into either equation. So I'm going to substitute it into the first one here. So then I'm going to sub G into the first equation to find H. So if G is 3, then minus 8 lots of G, which is 3, add 4H, add 52 equals 0. But then 4H and then minus 8 lots of 3 is minus 24, add 52, that's then 28, so plus 28 equals 0. So then therefore H is then minus 28 over 4, which is minus 7. There we are. So those are my values there. Cool. So I've got G is 3 and H is minus 7. Nice. Cool. Okay, let's have a look at this question. So we are given a function f of x. I'll probably note that down here. 4x cubed plus 4x squared minus 11x minus 6. Okay. And first of all, again, it needs to say use the factor theorem to show that x plus 2 is a factor. Where again, if x plus 2 is a factor, then the root would be minus 2. So f of minus 2 would equal 0 as a result. There we are. Okay. Right, so then I need to plug in minus 2 into the function, right? So then 4 lots of minus 2 cubed plus 4 lots of minus 2 squared minus 11 lots of minus 2 minus 6. Okay, then if I put all that in a calculator, I get I indeed get 0. There we are. Well, there we are. It's equal to 0. So f minus 2 equals 0. Therefore, x plus 2 is a factor. Cool. That's part A. Then part B then says factorise f of x completely. So again, it's very similar to the last early example. Right, so we know that this is one factor. So then we can say f of x then. Well, f of x is 4x cubed, right? Plus 4x squared minus 11x minus 6. So we know one factor of that is x plus 2. That's what we're proving in part A. But then the other factor then, well, if you have an x cubed and then we have an x, well, then it needs to be x squared. So it has to be a quadratic factor, right? So it's going to be ax squared plus bx plus c. Okay, a generic quadratic, right? We know it's a quadratic factor, but there we are. Okay, so now the mission is to find the quadratic, right? Exactly. What are the missing values A, B, and C? So again, then what we're going to do is expand it, right? Expand this bracket, and then it should match exactly the cubic. There we are. So if I expand it, I get ax cubed plus bx squared, and then plus xcx, and then plus 2ax squared, and then plus 2bx, and then plus 2c. There we are. So then again, now we're gonna compare coefficients, meaning equating the coefficients of all the x terms. But firstly, we got x cubed. So 4x cubed would equal the x cubed on the right hand side. So that would have to be ax cubed. Therefore, a would then be 4. Okay, very simply. Then we're going to do the same for the next term, the 4x squared term. So then 4x squared, the x squared part on the left, has to equal the x squared terms on the right. Well, we have bx squared, firstly, but we have the other x squared term plus 2a x squared. Therefore, then, if we equate the coefficients, we get 4 is equal to b add 2a. But we know a is 4, so it's 2 lots of 4. Therefore, then, we can solve for b. Then 2 times 4 is 8. So if we take away 8 to both sides, b is minus 4 there. Cool. Then lastly, we found a and b, we need to find c. Well, you can compare minus 11x and compare the x terms. We have cx and bx, 2bx. However, it's quite quicker to just compare the number at the end, right? So then minus 6 is equal to the number at the end here, which is just 2c. And then simply c is then minus 3 if I divide by 2. There we are then. So therefore, I got my factor to be f of x, which is our cubic, is x plus 2. And then a is 4x squared. Add bx, which is minus 4x. And c, which is minus 3. There we are. Cool. Okay, but then it says to factorise completely. So can I then factorise this quadratic any further? Let's have a look. So then we have 4x squared minus 4x minus 3. Well, again, we have a number in front of the x squared. It's 4, not 0. Not 1, sorry. So we need to consider numbers at times to get minus 12 from minus 3 times 4 and add to get minus 4. So then to help us with that, what are the factors of 12? Well, it's 12 or 1. They do not add or take away to get 4. What about the other factors, 6 and 2? Yes, we're in luck there, because if I do 6 take away 2, I get 4. Obviously, there's negatives, but the whole idea is I can get 4 in some way. I can then adjust for the negatives by making one of them negative. Well then, if I have 6 and 2, I need the times to get minus 12 and add to get minus 4. So one of them must be negative, but then it's going to be minus 6, right? Because minus 6 add 2 would be minus 4, and then minus 6 times 2 would be minus 12. So there we are, that's my pair. So again, this then splits up the minus 4x, because obviously they have to add to get minus 4, to then get 4x squared, take away 6x, plus 2x, take away 3. And then again, I factorise the first two parts and the last two. So then I can factor out 2x, and then that'd be 2x minus 3. And then simply we got 2x minus 3 there. And so that's a common factor, 2x minus 3. And then I'm left with 2x minus 3, and then 2x plus 1. So there we are. So then we can, if we get rid of this now, I can further factorise f of x to x plus 2, 2x minus 3, and 2x plus 1. And there we are. That's my full factorisation there. Okay, so that's part B. Then part C says, hence write down all the solutions to the equation. And that's the same function, right? It's 4x cubed plus 4x squared minus 11x minus 6 equals 0. Well, we've got our factors then, right? So if we're solving this f of x equal to 0, we're solving f in equal to 0. So again, that's each factor equal to 0. But therefore, the roots are x is minus 2 if you set the first bracket to 0, or 2x minus 3 is 0, so that means 2x is 3, x is 3 over 2. And the other one is when 2x plus 1 is 0, x will be minus a half. There we are. Cool. And that's part C. There we are then. Okay, let's move on to some exam questions then. Okay. So let's have a look. We are given a function f of x. which is 4x cubed plus 5x squared minus 10x plus 4a. We are given x minus a is a factor. We need to show this. So again, for part A, if x minus a is a factor, then that means x equals a is a root, right? Or in other words, f of a equals 0. If we plug in a into the function, I get 0, which is a root. There we are. Well, that's what we're going to do then. So therefore, f of a be 4a cubed, obviously x replaced for a, plus 5a squared minus 10a plus 4a. But actually, we can simplify that because I can collect the a terms here, firstly. Because then I have 4a cubed plus 5a squared minus 6a. And that's again going to equal 0 because a is a root again there. Well then, I can factor an a out because a is now common to all terms. So then I can say that's equal to a, lots of 4a squared plus 5a minus 6, and that's equal to 0 again, right? Well, there we are then. That matches what I got. A lots of 4a squared plus 5a minus 6 equals 0. There we are. Cool. Then part B says hence find the value of a. Well, we have an equation here, so we can use what we did here. So find the value then. Well, it's an equation, right, equal to 0. It's two factors, so I can set each part equal to 0. So either a is 0 or the other factor 4a squared plus 5a minus 6 is equal to 0. And because that's a quadratic equation, right? So I could solve that, say, via the formula. That would mean that a would be minus 5 plus or minus then the root of 5 squared. Take away 4 lots of 4, lots of minus 6, over 2 lots of 4. And then if I put that in the calculator, or at this point I can just be a bit cheeky and just put the numbers in the quadratic equation solving function in my calculator because I've shown them all working, so I'm confident to get all the marks. 4, 5 minus 6. I get the solution that a is 3 over 4 or minus 2. So overall then, I get the solutions a is 0, firstly, a is 3 over 4 or minus 2. Now I've got 3 possible values. Which one do I need to accept? Because it says find z value, so it's a singular. So in that situation, kind of look at the question and see what it tells you about a. And it says in the question where a is a positive constant. That means a has to be strictly positive, so greater than 0. Now, when it says positive in general, positive number means it has to be strictly greater, okay? Because then it has a positive sign, like positive 1, positive 2, positive 3. 0, I kind of see it like a neutral number. It doesn't have a negative or a positive side. It's a 0. It's this kind of special number. So if it's positive, then it kind of has to have a positive sign. So it does not include 0. It has to be above it. If, however, we said non-negative, then that means we just want numbers that are not negative. So that's the positive numbers here, but also 0 itself, because 0 isn't negative either. So that'd be then greater than or equal to. So if this says a was non-negative, then sure, a would be greater than or equal to. But here, if it's positive, it's clear that it means it has to be strictly above 0, okay? If it said negative, then it has to be strictly less than 0, to include like -1, -2, and so on, to have a negative sign. So I thought I'd mention that now, because it does come up, and you do need to know the difference, even though it seems quite particular, pedantic, but it does matter, even in this instance, because in this case, we have 0, so we need to reject 0 as a solution, because as a is positive, then we can only take 3 over 4, because the other two solutions, 0 and minus 2, are not positive. There we are. Okay, so then for the second part, it says, hence using algebra, find the exact solutions to that equation, f of x is 3. Okay, well now that we found a, then we can kind of substitute that into f of x. Well, remember, f of x had a 4a at the end there, so we can substitute that a in. So then f of x is 3 if I substitute f of x in. Then we get 4a cubed, 4x cubed, sorry, plus 5x squared, minus 10x add 4a. Now 4a is 4 lots of 3 over 4. That is just simply plus 3. Okay, and that's equal to 3. And then I can take away 3 to both sides, right? To then get, if I move it to the other side, to then get 4x cubed plus 5x squared minus 10x, and then 3 take away 3 is 0, so it's just equals 0 at the end. But I can solve this because then I can factor an x out right away. So then I get x of 4x squared plus 5x minus 10 equals 0. So then that means that either x is 0 or 4x squared add 5x minus 10 is 0. But actually, no, it looked very similar to the quadratic there, but it's minus 6 there. But however, in our example, we now have in this question we have minus 10. I thought we could reuse our workings, but it doesn't matter. Being able to solve it, it's quadratic. I can then use the formula again to then say that x would be minus 5 plus or minus the square root of 5 squared, take away 4 lots of 4 minus 10 all over 2 lots of 4. And so the other solutions, if I do that, gets me x is hang on a minute, 4x squared add 5x minus 10. There we are. Okay, I get the solution x is minus 5 plus or minus root, oh god, do I have room for this? 185 over 8. Okay, so it doesn't simplify very nicely, but the question does hint I'm going to get a nasty root because it said exact, which means it needs to be left as a fraction and surds and stuff like that. So we're going to have to leave it in this form. So overall then, my three solutions actually, if I get rid of this part now, are x is 0, x is that nasty fraction I got, which was minus 5 plus root 185 over 8. And x was minus 5 minus root 185 over 8. And there we are, those are my 3 solutions there. Cool, okay, let's have a look at this exam question then. Let me get rid of this now. It's getting in the way of the question. Okay, so we have this question then that says, the curve C1 has equation y is 8 minus 10x. Okay, they have 2 curves of these equations, right? I'm not going to say it out. First of all, it then says verify that when x is 1, the curves C1 and C2 intersect. And I will say this is a common exam question as well. Very similar sort of question I see multiple times. But okay, for this part then, it says verify that when x is 1, these 2 curves intersect. Now, when it says verify, it doesn't, that exam keyword there, it doesn't mean you have to show it, you need to prove it, you need to work it out. It literally just means check that is indeed the answer. It says check, basically. Well, how do we check it? Well, just plug in x is 1 into both the equations. So, when x is 1, firstly for C1, y would be firstly 8 take away 10 x, where x would be 1, plus 6 of x squared, it should be 1 squared, minus x cubed, it should be 1 cubed. So I put that in the calculator, I get y is 8, take away 10 lots of 1, plus 6 of 1, minus 1, I get 3, okay? So y is 3 at C1, and then at the other curve C2, y is an x squared, which is 1 squared, when x is 1, minus 12 lots of 1, plus 14, and so put that in the calculator, get 1 minus 12 plus 14, and indeed I get 3, okay? So at C2, so the y values are the same. Well, that means at the coordinate 1 1 3 is on the two curves. That same point when x is 1, y is 3 lies on both curves. So therefore we can say it lies on both curves. Now that means if two curves share the same point, remember, that means they intersect at that point. Well, there we are then. So they intersect. Therefore they intersect when x is 1. I should say when x is 1. There we are then. So very simple then, yeah. If it ever tells you to verify something like this, literally all that means is check that is indeed correct. So substitute it in, and then the equation should make sense, right? So there we are then. So they intersect then because the coordinate, the y and the x values are the same. Okay, cool. Then part B then, well, we're told that given k is less than, oh no, it says the curves also intersect when x is k. Given that k is less than 0, use algebra to find the exact value of k. Well, this is where the factor theorem will kick in, and you'll see. So, it's again talking about intersections again. Remember, it's been drilled into in various points of the course now. Intersecting means they equal each other, the two curves. So that means that if these two curves intersect, they equal each other. So I'm going to say when curves intersect, that means I need to equal the two equations. So substitute one into the other. I would then get x squared, say, minus 12x plus 14, which was the curve C2. Here, I'm going to substitute that for y into the top one. So then that's equal to 8 take away 10x. Plus 6x squared minus x cubed. Now I can rearrange this to get it look like an equation. So firstly, if I move the right hand side to the left side, I firstly get x cubed, and then x squared take away 6x squared be minus 5x squared, then minus 12x add 10x would be minus 2x, then 14 take away 8 would be plus 6 equals 0. There we are. So we need to solve this, and again on the surface, I don't know how to solve it, right? Because I can't factorise it in any way. So I need to essentially just plug in values and spot a root. However, this is where part A comes in, because it's talking about when x is 1 they intersect. Well, what that means is then, we already know one value of x when they intersect. That means x is 1 satisfies both equations. When that happens, if one value of x is on both equations like this, we've seen they satisfy both of them because they equal each other when x is 1. That means when we equal them, x is 1 will be a solution to that equation we get. Okay, and that is going to be a key idea here. So when we equate them together, kind of like simultaneous equations, because they intersect, because we already know one value of x when they intersect, we saw that in part A, but that was when x is 1. Well, that means it has to be a solution to this equation which stems from when they intersect. Okay, so if we equate them together, in this way, because they intersect, we know one value of x when they intersect. That means it's a solution to this equation. Okay, so that means x is 1 is a solution to here to this equation, right, that we've got here, because this equation again comes from them intersecting, and we discussed in part A, x is 1 is a solution to their intersection. They intersect when x is 1. We then need to find other points where they intersect, but we know one point. Well, that means if it's a solution, therefore x minus 1 is a factor of this, and that's where the factor theorem comes in. So it's a factor. I'm going to say by the factor theorem just to justify your answer. But there we are. So we know a solution to this, again, because of part A. So then we can deduce x minus 1 is a factor, okay, because of the theorem. There we are. That then allows us to then solve more complicated what's it called? More complicated polynomials like cubics. We haven't seen how to solve cubics, you know, in this sort of form. We can factorise if possible, but what if we can't factorise right off the bat? Well, then we need to resort to the factor theorem. So we might need to find a solution somehow, and then we can use that to find the other solutions. But there we are. What that means is then, if it's a factor, then we can again factorise it, right? So x cubed minus 5x squared minus 2x plus 6. We can factorise it to x minus 1, which is a factor, and then the other factor again, if we want x cubed, a cubic, well, we got x here, so it needs to be an x squared term, so it has to be a quadratic again. Okay, so we're going to resort to our comparing coefficients method we looked at earlier in order to factorise something in this way. But then let's expand it then, right? Expand this bracket, and it's going to equal this cubic here. Expand it, we get ax cubed plus bx squared, then plus cx, and then minus ax squared minus bx and minus c. And therefore then we can start to compare the terms of x. Firstly, x cubed, well, it's just 1x cubed, right? And then that's going to equal the x cubed term on the right. Now that's just ax cubed. Therefore, we can spot that a has to be 1. Okay, okay, well then what about the other, let's compare another term, minus 5x squared. So then what about the x squared terms? Well, it's bx squared here, and then an ax squared term there, so minus ax squared. Well then, we know a, therefore we can say if we compare the coefficients, minus 5 is b minus a, but a we know is 1, so that's just simply minus 1. Therefore, b would then, if I add 1 to both sides, b is minus 4. Okay, so then I lastly need to find c. Well then, I could again compare minus 2x, that's completely fine. Compare the x terms, but what about the number on the end? That makes it a lot easier. The number in the end is 6. So then 6 then has to equal the number in the end here, which would then be minus c. Therefore c is minus 6. There we are. So there we are. So now we've got the missing numbers a, b and c. So therefore we can factorise it to x minus 1, and then a is 1, so it'd be x squared. B is minus 4, so that's minus 4x squared. And c is minus 6. There we are. Okay, now if we wanted to, let's go back. If we wanted to, we could factorise it, but this question didn't say to factorise it. We'd just be doing unnecessary work there, because all it said is to find the exact value of, k when x is k. Well, that's just saying find the other values of x when they intersect, which basically means solve the equation when they intersect. So we don't need to factorise it and make it look nice, we just need to literally solve the equation. So remember, this will then be equal to 0, right? Well then we say bracket to 0, so that means when x is 1, or for the other part, x squared minus 4x squared minus 6 equals 0, but that I can solve by the formula. So then x would be minus 4 would be plus 4, plus or minus square root of minus 4 all squared, minus 4 lots of a, which is 1, c minus 6, over 2a, which is 2 of 1. Put that in a calculator, I then get x is 2 plus or minus root 10. Okay, so therefore I've got my three solutions there. 1, 2 plus or minus 10. Okay, now which one do I accept then? Which one should I take to be the actual solution they want me to take? Well, let's have a look then. So we already know x is one solution. Okay, but then it's saying it also intersects when x is k, this number k. We need to find k, and again it's find the exact value, which means fractions and thirds, right? Leave it in terms of a fraction and a third, which is what we got, right? We have 2 plus or minus root 10. We have a third there, so that's the exact value. Anyway, we need to find this value of k when k is 0. So basically, we need to find the other solution apart from 1. Okay, so the other solutions apart from 1, so not this one, it's indeed these two. Well, I've got two cases when it's 2 plus root 10 or 2 minus root 10. So that means the other solution k. Oh no, sorry, no, the other two. So x. So that we already have x is 1, right? We found that in part A. What's the other solution? So that means x is 2 plus root 10, or x is 2 minus root 10. Okay. Now, which one of those do we take? Well, it's this number k, right? The told us a particular root is k, and the told us k is less than 0. Well, therefore, then the value of k, the particular root we want, is when it's less than 0. So that means that k is less than 0. Oh dear. Therefore, we want to take the negative. Now that will be negative. 2 minus root 10 is a negative, right? So k would be equal to 2 minus root 10. There we are. Cool. Yeah, so hopefully that made sense then, right? So again, as I said at the start of this, it's a fairly typical exam question where they want you to intersect, when they want you to equate two equations or curves together because they intersect. Now, when you intersect them and equate them, you might get a cubic or something like that, but then you might need to use a factor theorem to factorise and break down the cubic into factors you can solve, okay, to find all the solutions and points when they intersect, okay, like we did here. So this x is 1 allowed us to consider the factor x minus 1 when we equate the two together to allow us to solve to find all the roots in that case. There we are. Okay. Final question then, final exam question. We have this. We are given f of x is minus 3x cubed plus 8x squared minus 9x add 10. First of all, calculate f of 2. Okay, that's fairly straightforward. F of 2 again, we just plug in 2 as x into our function. That will be minus 3 lots of 2. Actually, I won't have enough. We'll have enough room here. I have to squeeze it in. Minus 2 cubed plus 8 2 squared minus 9 lots of 2 add 10. There we are, just about. If I put all that in a calculator, then I get, and to be you can probably even guess what it should be given the question before we even do it, but let's put that in the calculator. And we get 0, which hopefully you did kind of expect, because then if it's 0, then it's a root, which means we can consider the factor. Now it's equal to 0. What's the significance of that? Then it says write it as a product of two algebraic factors. Now, again, hopefully it's talking about factors. Oh, I don't know why it's moved. I don't know why it's moved there. Anyway, it's talking about factors. Well, hopefully it's kind of ringing a bit of an alarm bell that we need to consider. We have to consider factors. Well, if we've got a root, then that screams factor theorem, right? Because if you know f of 2 equals 0, then that means, by the factor theorem, x minus 2 is a factor. Again, it's a factor of f of x here. Okay, well then therefore, as a product of two algebraic factors, well, okay, if x minus 2 is a factor of f of x, therefore f of x, which is minus 3x cubed, plus 8x squared, minus 9x plus 10, well, x minus 2 is one factor, and so then we need another factor. Now, again, similar idea to what we looked at in the previous few examples. If you have a cubic here, we have minus 3x cubed. We have an x term, so to get x cubed, we need a x squared factor. So we need a quadratic factor. So again, be ax squared, add bx plus c. And again, then our mission is to then find the missing values a, b, and c. How are we going to do that? Well, the left-hand side has to equal the right-hand side. So the best way to expand it, and then we go from there. So then, if we expand it, we get ax cubed, plus bx squared, add cx, and then minus 2ax squared minus 2bx minus 2c. Okay, but then again, once we got to this point, again, that both sides have to be equal. So if you compare each term of x, so firstly minus 3 x cubed, well, the x cubed parts have to equal, so we have ax cubed here. Therefore, to make them equal, a has to be minus 3. Then let's compare the x squared part, so we have ax squared here. So then the x squared parts on the right will be bx squared, and then minus 2a x squared. Therefore, that means 8, the coefficients are equal, so 8 is b minus 2a. Now a, we already worked out, is minus 3. So that's 2 lots of minus 3 there. Then we could solve for b, because then b would be, well, minus 2 times minus 3 is plus 6. So then 8 take away 6 would be 2. There we are. And then lastly, we need to find the last value c. Right, again, we could then do the x parts. You're well in your right to, but I want to make life a tad bit easier for me, and then just compare the number on the end, the 10. So then 10 would equal the number on the end here, which is just simply minus 2c. That's an easier equation to solve in that case. Then c is simply divided by minus 2 is minus 5. Therefore, there you can write f of x, which again is our cubic, is x minus 2, the factors on the right here, x minus 2, and then a would then be minus 3x squared, b is 2, so plus 2x, and c is minus 5. There we are, so those are the factors. Now, do we need to factorise any further with the quadratic? No, because it said the product of two algebraic factors. So we're completely fine. We don't need to simplify it anymore. These are two factors, which is what the question asked. So there we are. Cool. Then it says, using the answers to part A, II, for part B, prove that there are exactly two real solutions to this equation here, which looks a bit weird, okay? Now, hopefully you spot, and we did look at examples like this in chapter 2.1, when we looked at quadratic equations. This is a disguised quadratic. Hopefully you recognise there's some semblance of a relationship, a link between the two equations. And that's a disguised quadratic here, because we can express this as a quadratic. We can turn it into a quadratic by using by sort of comparing, right? Or no, it wouldn't be a disguised quadratic. It'd be a disguised cubic because it's a cubic here. But it's the same idea as we looked at earlier on in the chapter, in the course. Sorry, when we looked at disguised quadratics, where we have a sort of more complicated equation, but it simplifies to an equation that we know and we can work with, i.e., a quadratic that we know how to solve. Now, okay, so again, it says using the answers part A. Well, part A is for this function here, but I have a different equation here. Okay, but I can kind of see, right, it kind of matches, right, minus 3x cubed minus 3y to the 6. Okay, minus 3 minus 3, 8x squared, 8y to the 4, minus 9x minus 9y squared, 10 and 10 equals 0. So they kind of match, but how exactly then do I sort of connect them? What's the link exactly? I know there is a link vaguely, but what exactly? How can I write that? Well, let's compare it then. Well, simply then, I'd have to say x then is equal to something y, right? Because I can express this y in terms of x here to kind of connect the two equations together because they're disguised, right? This equation is a disguise of this. And we looked at examples like that again. Now, then, if I have minus 9x here, then minus 9y squared, but then x I can say is just y squared. Does that make sense then? Because if I have minus 3 of x would be y squared, if I plugged in x is y squared here, cubed, that'd be minus 3y to the 6. Well, hang on, there we are. What about if I plugged in at y squared for x squared here? Then 8 of y squared squared would be 8y to the 4. Well, there we are. So it does match. So that is my sort of substitution then, right? So with these sort of disguised equation questions, you want to use a substitution to link the two equations together. Okay. Now we have that. We know the link, the substitution. Okay. Now we can use our previous answer because we know how this solves for x. Right, we know how to factorize this equation for x, right? But we want it for y. We want it for y here. But if I know it for x, I can substitute this in for y using that, right? What I mean by that then is, for this question then, part B, I have x is y squared, right? That is the link between the two equations. Hopefully again, if I have if I put in minus 9x minus 9y squared, that means x will be y squared. That's the link how to get from the two equations. Okay. So if I want to consider the solutions to the equation here, I want to show there are two solutions, real solutions. Let's use our previous working. Well, if x is y squared, well, this is f of x, right? If I set this equal to 0, and then I can plug in, I can substitute this in for y. So what are the solutions for x then? Which will then, if I know the solutions to x, I can then find the solutions to y. So so I'm going to say f of x is 0, has roots. So each fat bracket equals 0. So no, sorry, that means x equals 2. Firstly, this bracket here, x minus 2 is 0, which means x is 2 is the root, or this other fat bracket minus 3x squared plus 2x minus 5 is equal to 0. And now I could use the formula, but I have a weird feeling you can use the formula to solve it, but I have a weird feeling there are no real solutions to this. How do I check that? Well, I'll just use the discriminant, right? B squared minus 4ac, that's going to be b squared would be 2 squared. Try to go 4 lots of minus 3 minus 5. If I put that in the calculator, I get minus 56. There we are. That's less than 0. What does that mean? That means I'll know there's no real solutions to that quadratic. That means the only solutions when f of x is 0 is just x is 2. So now we found the only solutions for x, well then we know to solve the other equation, that y, that the equation up here, in terms of y, but we know it's a disguised equation because I can link the two by saying x is y squared. Well then I need to solve for y, not for x, but I know if x is y squared, therefore the y squared equals 2 only. Okay, so that means y is plus or minus root 2 are the solutions, right, to the equation they described. Therefore, because there are only 2 solutions there, 2 real ones, well then simply there are exactly 2 real solutions to the equation. They described there, right? The 2 real solutions, and we found that because well, we've got 2 solutions, right? Plus or minus root 2. But yeah, so that's factor theorem then, right? And hopefully you've seen it can be quite useful to factorize stuff, to then solve equations and sketch the graphs and so on. But the idea is very simple, right? To recap, if we have a factor x minus a, that means f of a is 0, so a is a root, which again stems from setting the bracket to 0 to get x is a. And alternatively, if we then on the flip side that had a root a, which is 0, then we can then deduce x minus a as a factor in that way. Okay, so that is the factor theorem. I'll scroll up to remind you again what we wrote. Where did we write it? Yeah, we wrote it. This is the factor theorem there. But yeah, that is the factor theorem. So hopefully that has helped. But yeah, I will see you next time.